Hello everyone from Math 1340, Statistics. Professor Wenson here again with a video on your KnewtonAlta homework for section 6.2 titled Using the Normal Distribution. So in this video we're going to see how to find probabilities when we're talking about a normally distributed random variable. Right, that means a variable whose probability density curve is one of those symmetrical bell-shaped curves that you saw in section 6.1 for a normal distribution. And if you recall, for a continuous random variable, probability will correspond to area underneath the curve. Okay. So the first objective I'm looking at here is use the empirical rule for normal distributions to estimate probability. Now you've seen this before. I can click on more instruction here, but I'm just going to draw you a picture. You've seen the empirical rule before when it comes to normal distributions. It was also referred to as the 68, 95, 99.7 rule. So I'm going to go to a piece of paper now and draw a little picture for you. All right. So remember, suppose that we have a random variable x, and I've drawn this picture in previous videos, my last video actually in section 6.1. And suppose this random variable x is normally distributed. All right, so remember the notation for this, the capital N there, with a mean value of mu or mu sub x and a standard deviation of sigma or sigma sub x, either way. Then the probability density curve for a random variable that's normally distributed looks like this, right? So I have a number line representing possible values of capital X, and above that a symmetrical bell-shaped curve. Now again, I'm going to try my best to keep this looking pretty even. And it goes to the left forever, to the right forever. And this is a bad hand drawing. It should be perfectly symmetrical. All right, if I cut it down the middle, the area to the right half is the same as the area to the left half. All right, and if you look at this, all right, underneath the top of the hill, you go to the peak, directly underneath that, on the number line should be the mean value, or will be the mean value of the variable x, which is called mu. All right, so that's on the number line. And then I've brought this up before as well. There are these things that are inflection points. There are points on the curve where it changes the way it's curving. It's called concavity. See how it's curving downward, and then at some point it starts curving upward. Right? The curve is pointing down here, the curve is pointing up here, curling up. That's an inflection point, and there's one exactly the same distance on the other side, right? It should be perfectly symmetrical. The value on the number line beneath these inflection points should be one. Now again, these should be the same distance, should be one standard deviation away from the mean. So this value under this inflection point to the right will be at mu plus one standard deviation. And over here under the inflection point to the left will be at mu minus sigma, right? Mu minus one standard deviation. All right, and then I'm going to try to make each notch about the same space apart. So there's another standard deviation, and another standard deviation, and do the same over here. There's another and another. All right. So this is 2 standard deviations above the mean, this value on the number line, so mu plus 2 sigma. This value is 3 standard deviations, mu plus 3 sigma, right, above the mean. Here's 2 standard deviations below the mean, so mu minus 2 sigma. And here's 3 standard deviations below the mean, mu minus 3 sigma. Okay. And this kind of breaks the area under the curve up into some regions, right? Let me make this a little longer over here. Right. Now remember, the entire area, right, from the far left forever to the far right forever, the entire area under the curve, under any density curve, right, the total area or the entire area is 1, right, 100%. I'm going to do some different colors here to denote different areas. Now the empirical rule, remember that stated that the area under the curve, a normal curve like this, these symmetrical bell-shaped curves, the area under the curve within 1 standard deviation, so from mu minus sigma to mu plus sigma, that area there is approximately 68%, or 0.68. Again, the area under this curve from mu minus sigma to mu plus sigma is approximately 0.68. Let me take a different color. Here we go. Then within 2 standard deviations, right, so if I do this area here, right, so from mu minus 2 sigma to mu plus 2 sigma, the area under this curve is approximately 95%, right, or 0.95, 95%. That was within 2 standard deviations. Right, so maybe I should write this out. This is within 1 sigma, right? This area I've written here is within 2 sigma, right? All right, and then the area within 3 standard deviations. So from mu minus 3 sigma all the way to mu plus 3 sigma. So this area here, right, I'm just cross-hatching the other way. Right, this whole area in this color is approximately 99.7% of the entire area, so 0.997. And this is within 3 sigma, right, 3 standard deviations. And again, then you got these tiny little areas on the far right and the far left that are blank here. That makes up the last 0.3%, so 0.15% over here, 0.15% over there, all right, to make the entire area, 1 or 100%. So that was the empirical rule, all right. And you can use symmetry also. Right? You can use symmetry to find the area between mu and mu plus sigma. Would be about 34%. From mu to mu plus 2 sigma would be half of 95%, so 47.5%, and whatever. You can find the area under the curve between any of these special values using this empirical rule, using these numbers. All right, so let me get to this problem here. All right, see how we're going to use this, and I'll keep drawing up lots of pictures of bell-shaped curves, all right, to help us find these out, find these probabilities. All right, so here Brenda has collected data to find that the finishing times for cyclists in a race has a normal distribution. All right, so what is the probability that a randomly selected race participant had a finishing time of greater than 154 minutes if the mean time is 143 minutes and the standard deviation of the times is 11 minutes? All right, so I'm going to write all that out again on a separate sheet of paper and draw you a picture. And I'm going to be drawing this picture of a bell-shaped curve quite a lot. All right, so in this particular problem, all right, I'm going to call x, all right, I'm going to have x be these finishing times. All right, the finishing times for these cyclists for this race. And we're told, right, we're told that this, this set of finishing times for all the racers is a normally distributed random variable, or approximately normal, with a mean of 143 minutes and a standard deviation of 11 minutes. And so now that I've got this information, I'll draw a little density curve, probability density curve. So again, here's a number line representing different possible values, different possible finishing times. And above this, I'll make that, this symmetrical bell shape. It's normally distributed. And that way forever, that way forever. They told us the mean value, right? So underneath the peak here, this value on the number line should be 143 minutes. Right? And they told us that the standard deviation of all these finishing times is 11 minutes. So under this inflection point and this inflection point, this is a distance of 11 minutes. And 11 minutes above the average, 11 minutes below the average. So 143 plus 11 is 154. That'd be one standard deviation above, one standard deviation below. 143 minus 11 would be 132. So again, here's mu plus 1 sigma. Here's mu minus 1 sigma. And I can keep going, right? So again, go another standard deviation here. So let's say this is 2 and this is 3. Again, trying to keep things evenly spaced here. Say here's another standard deviation. Let's say that's 2 to the left and 3 to the left. And I'll make these little section them off. Right? And just keep adding and subtracting 11, right? So 154 plus 11 is 165 plus 11 is 176. So here's mu plus 2 sigma. Here's mu plus 3 sigma. And then 132 minus 11 is 121. There's mu minus 2 sigma, and then minus 11 again would be 110. There's mu minus 3 sigma. Okay? Now what we are asked to find, we're asked to find the following probability. They want us to find the probability that a randomly selected race participant had a finishing time greater than 154 minutes. So find the probability, remember the probability notation, probability that a random finishing time, right, that the value of x is greater than 154 minutes. Find this probability that a finishing time is greater than 154 minutes. So I'm going to highlight that with an area. Remember, probability will correspond to an area under the curve. So 154 minutes is here on the number line, right? And that corresponds to this point on the curve. And then greater than 154 minutes is this way, forever, right? So we're talking this area. And it's forever, to the right forever. Okay, so using the empirical rule, remember we said that from here to here, remember within one standard deviation is about 68%. Meaning that the area over here to the left, from mu minus sigma, from 132 to the left, and from 154 to the right, those have to add up to 32%, right? Because 68 plus 32 would be 100%. So the area to the left of 132 and the area to the right of 154 have to be 32%, meaning that this is approximately 16% over here, and that means that this is approximately 16% over here as well, to make a total of 100%. Right? So the probability that the one area we're finding, according to my picture here, is approximately 16% of the area. All right, so this probability is approximately 16% or 0.16. Sorry, 0.16. Forget that decimal point. 0.16. Okay? It's that simple. All right. I would recommend drawing a picture, actually. All right. And they said write it as a percentage, right? So 16. Wonderful. Okay. All right, so this is, again, use the empirical rule. So again, I will draw a little picture. Right. So here, the number of pages per book on a bookshelf is normally distributed. Suppose that it is, with a mean of 248 pages and a standard deviation of 21 pages. All right, so using the empirical rule, what is the probability that a randomly selected book has less than 206 pages on this, this bookshelf? And provide the final answer as a percent rounded to 1 decimal place. All right, so the nearest tenth of a percent. All right, so again, I'm going to go to a piece of paper and draw a picture of a curve like this. All right, so again, now this time I'll say my random variable x represents these, number of pages in a book, right? So numbers of pages in a book. And we are told that this number of pages per book here is normally distributed with a mean of 248 pages and a standard deviation of 21 pages. All right, so I'll draw a density curve for this. A number line representing possible numbers of pages, right? The possible values of x. It's a normally distributed random variable, so above this, a symmetrical bell-shaped curve. Again, I'm trying my best to make it look symmetrical. Going to the right forever, left forever. Beneath the peak, right, beneath the very top, the value of x here is, the mean, 248. And then I'll mark off, 1 standard deviation above and below at these inflection points. All right. So that's 1 above, 1 below, and then we'll go, here's say 2 above, and then 3 of those, 3 standard deviations above, and then 1 below, two standard deviations below the mean, 3 standard deviations below the mean, and I'll mark off what these values are. Now the standard deviation is 21, right? So I'm just going to keep adding and subtracting 21 to get these special values on the number line here. Now 248 plus 21 would be 269. Plus 21 again would be 290. Plus 21 again would be 311. All right, and those are all 1, 2, and 3 standard deviations above the mean. Then below 48, minus 21, it'd be 227. Minus 21 again would be 206. Then minus 21 again would be 185, right? That's again 1, 2, and 3 standard deviations below the mean. Right? Okay, and we're asked for the following probability. We're asked to find what's the probability that if I pick a book at random on these bookshelves, what's the probability that a randomly selected book has less than 206 pages, so that the number of pages that x is less than 206. Remember, this corresponds to an area, right? That area, first, where is 206? That's here, right? On the number line, 206 corresponds to this point on the curve. We're looking for the probability that x is less than this. Well, less than 206 is over here, forever. So we're talking this area forever, right? Okay, but using the empirical rule, we know that from here to here, right, from these, this is 2 standard deviations, right? From 290 to 206, it's approximately 95%, right? 95%. That means that this area over here to the left of 206 and this area over here to the right of 290 have to add up to 5%, right? Because there's 95% between 206 and 290. The other 5% have to be outside that, right, to make a total area under the curve of 100%. So this area to the right of 290 is approximately 2.5%. And so would this area over here to the left of 206, approximately 2.5%. So the probability that you pick a book at random, if the numbers of pages are truly normally distributed with a mean of 248 and a standard deviation of 21, if I picked a book at random, the probability that that book would have less than 206 pages is approximately 2.5%, or 0.025. But I think they want it as a 2.5%. They want it as a percentage. So I'm just entering 2.5 there. Wonderful. So again, I would recommend drawing a picture and marking off, where the 1, 2, and 3 standard deviations above and below the mean are. Okay, now we're getting into a new objective. Now in this objective, we're going to be looking at tables. All right, tables that help us find, that show us areas under a normal curve, a bell curve. I'll show you how to read. I'll talk to you about how to read these tables. So we're asked to use the normal distribution to, again, compute probability. Now notice the letter Z showing up here. So remember, Z was for the standard normal curve, and you saw that in the previous section. The standard normal distribution has a mean of 0 and a standard deviation of 1. That was the standard normal, the Z distribution. Okay, so we're asked here to determine the area under the standard normal curve that lies to the right of the Z-score negative 1.12 and at the same time and to the left of the Z-score negative 0.79. And use the values from the table above. Now, I will tell you right now, you find your Z-scores on the margins, right, the top row and the left column. So like negative 1.12, I go to negative 1.1, that's the second row. And then the hundredths place is 2, so I go to 0.02, 2 in the hundredths place. So I go down to the second row for negative 1.1, and then 2 in the hundredths place, I go to the third column here. So negative 1.12. This 0.1314, all these numbers inside the table and the bulk of the table represent areas to the left. They represent areas to the left of that value. All right, so let me show you what I mean with a piece of paper. All right. So now we're looking at the standard normal. Remember, that was the Z, which was normal with a mean of 0 and a standard deviation of 1. So I'm going to draw a similar picture. And now these are possible values of Z on this number line. possible z-scores. And a symmetrical bell-shaped curve above it. Right forever, left forever. Underneath the peak, 0, right? Mean of 0. And a standard deviation of, 1. So underneath these inflection points, those are the values 1 and -1, right? And you could mark off where 2 and 3 and -2 and -3 are, right? 2 and 3 standard deviations above, 2 and 3 standard deviations below. But now we're not looking at whole numbers of standard deviations, right? Again, look back at the website. We're trying to find the area between -1.12 z-score and -0.79. These are not nice whole numbers. All right. Again, back here. So I'll mark off where these are. All right. So now, we're going between -1.12. So that'd be over here somewhere. So let's say that's here. -1.12 z-score and -0.79. So let's say that's about here. -0.79. And we're asked to find the area between these. They said to the right of this and at the same time to the left of this. So we're finding right now the area under the curve between these two values. All right, so we want to know what's the probability that our z-score here is between -1.12 and -0.79. This is the probability we're finding. Sorry about the clutter there. It's -1.12. All right. So how do we now, using a table, using these tables? Now, careful. Like I said, the tables give you areas to the left only. They give area to the left only. All right. So let me show you what I mean. So looking back, all right. So let's take a look at, say, -1.12. Let me go to that table, and I'm going to find the z-score of -1.12 and see what number is in line with that z-score. So again, I go -1.1 on the left column here, and then 0.2 is the hundredths place. And then -1.12, sorry, -1.12 has this right here, come on, right there. See, that's the score that I'm seeing, 0.1314. So 13.14%. Again, these numbers in here are areas to the left. So 0.1314 represents the area under the curve to the left of -1.12 z-score. So back on my paper, I'll mark this off in a different color. All right. So here's -1.12. This area, okay, this area to the left that I'm shading in here. That's really light. I apologize. Let me grab a different marker. So this area to the left of 1.12, this area is approximately 0.1314, and this was from the table, right? This was given to me from that table. All right. Now, that will help us. As I look up the value on the area to the left of -1.12 is 13%-ish, 13.14%. Now all I need to do is look up this other score, -0.79, -0.79, get the area to the left of that, and then subtract this area, and then we'll have the area in between these two. I hope that makes sense. Right? If I take the area all the way to the left of -0.79 and subtract the area all the way to the left of negative 1.12, you see I'll be left with this area in between, right? We're gonna subtract these areas. So I got 0.1314 for the area to the left of negative 1.12. Let's look up the area to the left of negative 0.79 on that table. So I go z negative 0.79. All right, so I go to 9 in the hundredths spot. That's the last column. So now I'm here. Negative 0.79, 0.2148. So the area to the left of z equals negative 0.79 is 21.48%, or 0.2418. So back on my paper. So this area is 0.2148, right? This area to the left of 0.79. This area is 0.1314, the area to the left of negative 0.112, negative 1.12. And I subtract those and I'll get the area in between, right? I'll be left with this area in between here that I'm looking for. Now a way to write this in probability notation is I'm taking, what's the probability that, z is to the left of negative 0.79, right? That's this area here, the 0.2148 from the table, and then I subtract the probability that z is less than negative 1.12, right? The area to the left of negative 1.12, and that was that 0.1314, right? So in subtracting these, and I'll set up a little column here. So, we got 4, 3, 1, 8, 0.0834. So this is equal to 0.0834. Right, so this area here, 0.0834, that's the area in between the z-score of negative 1.12 and negative 0.79. So this little area in here is a little more than 8% of the entire area under the curve. But that's how you read these tables. All these numbers in here are areas to the left of whatever z-scores you're looking at. All right, so they ask us to provide your answer below. Right? And now notice how all these areas are to 4 decimal places, and they didn't say anything specific. So just enter areas like they are in the table to 4 decimal places, and that was the 0.0834, right, like I said. You can see there, area to the left of negative 0.79 minus that area to the left of negative 1.12. Okay. Now a much quicker way to do this, right, and I'll show you on the calculator. A much quicker way to find this probability on the calculator is this. Right, let me pull the calculator up. Now again, this is an 84 plus. You can use 84 plus, 83. They're both pretty similar. If you look at, there's a button that says vars, right? Variables. Right above that it says distra, D-I-S-T-R. You've seen that for, I've used that for the binomial probabilities, right? Remember binomial distributions? Well, there's also a way to find probabilities under normal curves under distra. So I go second, and then above the vars button is distributions, right? And now you see right up top, number 1, number 2, there's normal PDF, normal CDF. Now when we're finding area under a curve, we're accumulating area, cumulative. So you can use normal CDF, right? So I'm going to write this down here. So for this probability on the calculator, I'm going to put in this normal CDF, right? Let me show you what pops up here. So I'm going to go down to 2, normal CDF. Now I ask you, what's the lower value in the region? What's the lower, now in this region here, see the lowest value. Now the region is the orange region here between negative 1.12 and negative 0.79. The lower value is negative 1.12. So I'm going to enter that, negative 1.12. And that'll be the first value that shows up on the screen. You'll see negative 1.12 and then a comma. So if you're entering on an older calculator, you'll see normal CDF pop up, you enter the lower value of the region first, comma, then the upper value. The upper value in this region is negative 0.79, right? So I'm going to type that in. So negative 0.79, then a comma. Now you can just leave it on the old calculators because it automatically assumes that the mean is 0 and the standard deviation is 1. It automatically assumes on the old calculators that you're working with the standard normal, right? The z-scores. But you see here on these newer ones, you got mean, mu, what's the standard deviation? Well, it's the standard normal, so mu is 0, so I have 0, comma, and then the standard deviation is 1. So I'm just going to, and then close parentheses. So I'm going to leave that at 0, leave that at 1, and you see what happens. What gets pasted up here is what I've written down here at the bottom of the paper. So I'll scroll left here and show you. So you have normal CDF, then you have the low value in the region, comma, the high value in the region, comma, the mean of 0, or whatever the mean is, right? For the standard normal, the mean is 0 and the standard deviation is 1. You can put in different means and different standard deviations for different normal curves, and we'll see that later. All right, and then we get our area here. Now see, it's 0.08340. Look at the first 4 decimal places, round to the 4 decimal, 0.0834. Hey, that's exactly what I found, using that table. Okay, so much quicker. If you want to use that, that's fine too. All right, to find area under a normal curve, this normal CDF. And well, I'll come back to that, of course, in future problems in this assignment. All right, so let's continue on. So another question, same objective here, use the normal distribution to compute probability. Right. So this is determine the area under the standard normal curve that lies to the right of 0.48 z-score, again standard normal, so z, and to the left of z equals 0.79. All right, so again I'm going to draw a little picture and set this up. Let's get rid of the calculator for a second. So again, we're working with the standard normal curve, right? That z normal distribution with a mean of 0, standard deviation 1, number line, possible values of z, got a symmetrical bell curve above it. Right. The mean value is 0, right? So right below the middle here, there's 0. Standard deviation is 1, so underneath these inflection points is 1 unit above, 1 unit below, right? And these should be, this is a bad drawing, right? But they should be the same distance apart. All right. Now we're asked to find the area, under this curve to the right of the z-score of 0.48. 0.48 is mentioned, so there's this z-score. And then 0.79, so a little bit more than that. Still between 0 and 1 though. All right, so we're talking this area right here, this tiny little strip. What's that area? All right. Again, a way to write this would be, what's the probability that z is between 0.48 and 0.79? Right. Now what we're going to do is use our I'll use the table first. So what we're going to do is I'm going to look up 0.79, find the area to the left of that, look up 0.48, find the area to the left of that, and then subtract, right? Just like the last problem. And then that'll give us the area in between that I want, right? So I'll write this as the probability that z is less than 0.79. And then we're going to subtract the area to the left of 0.48, the probability that z is less than 0.48. And I find these on my table. All right, so 0.79. Right, the first value I will look up is 0.79. 0.7 on the left, and then 9 is the hundredths place. So 0.79, that's giving me this number here. 0.7852. So 0.7852. 0.7852. That's the area to the left of a z-score of 0.79. Right, so back on my paper, so this is 0.7852. This, from here onward to the far left, is 78.52%. All right, now I'm going to look up the z-score of 0.48. So 0.4 on the left, and then to 0.08 here. That's this number here. Come on. All right, 0.6844. So the area to the left of the z-score of 0.48 is 68.44%. And we're going to subtract these. Right? So again, this is 0.6844. So I got 0.7852 minus 0.6844. I'll stack them. 0.7852 minus 0.6844. Got to borrow here. It's 8001. So 0.1008. So a little more than 10%. Yeah, 0.7852. Yeah, minus 0.6844. Great. So a little more than 10%. I know it doesn't look it because it's it's a hand drawing. That doesn't look like 10% of the whole thing, but it's a hand drawing. I didn't do that great a job. But it should be a little more than 10%. All right, now I could have also again brought the calculator up, and if you want, I would try doing this by hand. Try doing this with the tables at least once, just to get used to reading the tables. Let me go to the calculator here. So again, I go to that second distributions, normal CDF, right? Normal CDF. The first value I'm going to enter is the lowest value in this region I'm trying to find the area of, which is 0.48. So 0.48. The upper value in this region is at 0.79. 0.79. Mean is 0. Standard deviation is 1. And see this 0.1008. And that would round to 0.1008, which is what I had here using the table. Okay, now if for some reason it rounds, you might be off in the last decimal place when you use the calculator, because all the values on this table, right? All the values on this table are rounded values. They're rounded to the fourth decimal place, to the nearest 10,000th. So if you're off in the last decimal place, it'll in the calculator it'll mark you wrong here. Just go back and do it in the table, right? Because they want an answer. They're throwing the table at you, so they're assuming that you're using the table. So using the table here, I've got 0.1008 as the probability that you fall between, z equals 0.48 and z equals 0.79. Okay. All right. This is another empirical rule 1. Now, and you could use your calculator here to help you. I mean, the empirical rule is not hard to remember. So again, I'm going to draw a picture, but I'll show you how you can enter something on your calculator to help you out as well. All right, so here, after collecting the data, Tammy finds that the total snowfall per year in Lindale is normally distributed with a mean 99 inches and standard deviation 13 inches. So what is the probability that in a randomly selected year, the snowfall for that year was greater than 112 inches? So again, I'm going to draw another picture. So I'll get rid of the calculator for a second. So this isn't the standard normal, right? The mean wasn't 0 and the standard deviation wasn't 1. So I'm not going to call it z, I'll call it x, right? Now let's say x here is the snowfall in a year. Right? This is the snowfall in a year. And they're telling us that x is normally distributed with a mean value of 99 inches and a standard deviation of 13 inches. I'll draw a picture. Here's a number line with possible different snowfall values of x. the distribution, symmetrical bell-shaped curve above this. Oop, I had a groove in my table. Sorry about that. I'm drawing this on some wooden table here. A little divot there. The mean, right, the value underneath the peak, that's 99 inches of snowfall, and then these inflection points on both sides. They're hopefully, again, I'm trying to keep them same distance apart. That's 1 standard deviation, then 2, then 3, and then this is 1 standard deviation below, and then say 2 and 3. Trying my best to keep all these evenly spaced. All right, and these values, right, the standard deviation is 13 inches. So I'm going to keep adding and subtracting 13. So 99, plus 13 would be 112. Plus 13 would be 125. Plus 13 would be 138. All right, so there's 1, 2, 3 standard deviations above the mean. Then below, 99 minus 13 would be 86. 86 minus 13 be 73, and 73 minus 13 would be 60. And now here's 1, 2, 3 standard deviations below the mean. And we're asked to find, what's the probability that if she picks a year at random, that the snowfall that year was greater than 112. So remember, snowfall in a year is this x here. So what's the probability that x is greater than 112? All right, so if I draw a picture of that region here, now 112 is here, and we're talking this area, right? Greater than 112 is going that way forever. Now we did something like this already, right? This is just 1 standard deviation above. Now remember, with the empirical rule, between one standard deviation above and 1 standard deviation below is approximately 68%. So then the area outside that is about 32%, meaning that there's approximately 16% over here and approximately 16% over here to make a total of 100. Now, I could have also used a calculator. So this probability is approximately 16%, right? Or 0.16, 0.16. Let me pull the calculator up and show you also another way you could have figured this out. I turn this on here, and now again, I'm finding area under a normal curve, normally distributed random variable density curve here, a bell-shaped curve. So again, let me clear this. Again, I go to that second distributions normal CDF. All right, now what's the lower value? Now look at the region, right? I've shaded it in here in orange. The lowest value in this region is 112. So I go 112. Now, here's the tricky part. What is the upper value in this region? Well, there is none. See how this goes to the right forever. This is the area to the right of 112. So if there is no upper value, I'm just going to put a really large positive number here for upper value. Something that's very far away from the mean, right? Remember, 3 standard deviations away is pretty far away. I want something that's a lot, 100 standard deviations away. I'm just going to put a very large, so like say 9, 9, 9, 9, 9, like 5 nines, something really far away from the mean. Okay? To represent that there's no upper value. All right, and then I would, if I was doing the left, I would do the same thing with a lower value. If there was no lower value, I'd put in for the lower value, negative 99999 or something, right? Some big negative value that's clearly way far away from the mean. All right, now the mean is not 0, right? This is not the standard normal. This is just some other normal distribution. The mean was 99 inches, right? So I entered 99. The standard deviation, 13, not 1. So here's how it's going to look, on the older calculators. You enter, again, the normal CDF pops up. You put the lower value, 112. You put some big positive number for the upper value because there is no upper value. Then you separate these with commas, and then you got the mean 99, comma, the standard deviation 13. Look at this. See, 0.158. 0.158. What would that round to? Right? That in 2 decimal places. That rounds to 0.16. Right? If I rounded to 2 decimal places like I have here, that rounds to 16%. So you could also have the calculator do this as well, right? You would have come up with the same value. Now, it's the empirical rule, not hard, right? 68, just remember the 68, 95, 99.7 numbers. So this again would be about 16% greater than 112 inches. Okay, another empirical rule one. This one has less than something. So I'm going to pull the calculator up here. We can figure this out right now. So I pull the calculator back up. All right, so now instead of drawing a picture this time, all right, yeah, let me actually read it first, then pull the calculator up. So after collecting the data, Douglas finds that the finishing times for cyclists in a race is normally distributed with a mean, so the middle is at 149 minutes, standard deviation is at 16 minutes. What's the probability that a randomly selected race participant had a finishing time less than, so this would be to the left, 165 minutes. All right, now 165, 149 is the middle. 165 would be 149 plus 16, so that's one standard deviation above. So that's everything to the left plus one standard deviation above. That's another 34%. This is about 84% if I'm using the empirical rule. All right, again, you can draw a picture. Now I could also do this on the calculator. I pull the calculator up and go second, distributions. I'm finding area under a curve, normal CDF, normal curve. Now this time we're going less than 165, so there is no lowest value. So I'm going to put some big negative number, negative 99999. Why not negative 59? Some big negative number indicating to me that there's no lowest value, something that's very far away from the mean. Now the upper value, we're going to the left of 165 minutes. All right, so the upper value in the region would be 165, and again, you can draw a picture if you want. See that the upper value in the region is 165. The mean value was 149 minutes, right? And the standard deviation was 16 minutes. I enter this and see it pops up 0.841, rounds to 0.84, right? 84%, like I said back in my entry here, right? So however you do it, it should be this, should round to the same thing, or if it, and if it doesn't, it's usually off just in the last decimal place by 1 unit. So you can use a calculator if you wish to help you out, but again, empirical rule is not crazy difficult, I don't feel. All right, so we got that done. All right, so again, this is more table reading. So I've already done 2 problems like this. I'll leave this to you. I'm just going to put in the instructor cheat. I've already done 2 problems like that. And again, you can use your calculator to help you out too. And again, if it's wrong, if you use your calculator and it ends up being wrong, that means it's off in the last decimal place. So because they want you to use the table values. So if it's wrong with the calculator, that just means the last decimal place is off by 1. Go use the table values instead. All right, so let's see. This is another one like that. All right, now this time though, all right, this one I'll draw. See, they want the area to the right of just one z-score, and they throw us a table here of 0.03 under the standard normal curve, right? So again, I'll draw the standard normal curve. So remember z, that's the z, right? That's normal with a mean of 0, standard deviation of 1. So number line, possible values of z. Got a symmetrical bell-shaped curve above it. The mean is at 0. These inflection points are 1 above and 1 below, right? And so on, right? Now we're asked to find the probability or the area to the right of a z-score of 0.03. So let's say that's here, 0.03. And the area to the right of that, right? All of the area to the right, so all the way to the right forever. Right. Now remember, if I'm using that table, All right, if I'm using that table, if I look up 0.03 on a table, it gives you the area to the left. All right, the table will give you this area, the area from 0.03 to the left. So how do I find this? Remember, the total area, the entire area under the curve is 100%. So if you look at the table for 0.03 and find the area to the left, just subtract that from 100%. Subtract that from 1, and you'll get the area to the right, and I'll show you what I mean. So on the table here, so I look up 0.03. So 0.03, so that's this number right here, 0.5120. So this is the area to the left of 0.03, 51.2%. It's on the paper. This is 0.5120. This area here, 0.5120. All right. That's the area to the left of 0.03. So this plus this should be 1. So I just subtract this from 1. All right, subtract from 1. So this area here to the right of 0.03 is 1 minus 0.5120. So this is 0.487. That is 0.488. 0.4880. All right, if you add those up, 5120 and 0.4880, you'd get 1. All right, 100%. That's all. All right, but again, you just got to remember that the table values give you areas to the left, right? So if they're asking for areas to the right, you're going to have to subtract it from 1. And again, you could have had the calculator help you out here. Right, the calculator value. Let's see what happens when I do my calculator. So again, back to that second distributions normal CDF. Now this time the region I'm looking for the area, right, does have a lowest value of 0.03, right, so 0.03. It has no upper value, right, it goes to the right forever. So again, I'm going to put in some very, very large, 5 nines or whatever. Put in very, very large positive number, something that has many, many standard deviations to the right of the mean. All right, now this time it is the standard normal, so mean is 0, standard deviation is 1, and you see 0.4880, and then 3, and that would round down to 0.4880, which is exactly what I got using the table. All right. So back here, and enter 0.4880. Wonderful. So again, now the last two objectives are using the calculator. Now I've already shown you how to use the calculator to find area under the curve. One of the objectives is, if you're given an area, can you find the values on the number line? All right, so when I get to a problem like that, I'll show you. Yeah, so this is use the normal distribution to compute probability with technology, right? So this is just like I've been showing you. Find the probability. They give you a mean, they give you a standard deviation, you just got to read it, right? They say find the probability that a household personal computer is used for entertainment between 2.1 and 2.45 hours per day, where this number of hours of entertainment is normally distributed with a mean of, well, let's see, a mean of, the average number is 2, and the standard deviation is half an hour, 0.5. So here's what I enter. After just glancing through this, I'd go second, distributions, normal CDF. We're finding the probability of having between 2.1 and 2.45 hours of entertainment per day. So lower value, 2.1. And you could draw a picture if you want, like with the bell curve and all that. Upper value, 2.45. They said the mean, the average was 2 hours a day. The standard deviation was half an hour a day, so 0.5. And I enter this, and it's all the same. So, and then round to 4 decimal places. So it says here, 0.23668. So 0.2367 if I'm rounding to 4 decimal places. So a little over 23%, right? 0.2367. And they show you the same thing. How I entered it on the calculator there, they're showing you that down here. All right. So I've already shown you that. If any other problems like that come up, I'm just going to give you the instructor cheat then. Yeah, so this is the same kind of problem. So gonna cheat on that. Move on. I want to get to that last objective where you're given an area under the curve and you're asked to find the value on the number line. All right, so here we go. This is it. Use the normal distribution to compute a value for a random variable given the probability, right? So here you're given the probability, you're given area, and you're asked to find the value on the number line. All right, so I'll read through this one, and again, I'll draw a picture and show you how we're going to use the calculator to help us find these. All right, so see, a credit card company receives numerous phone calls throughout the day from customers reporting fraud and billing disputes. Most of these callers are put on hold until a company operator is free to help them. The company has determined that the length of time a caller is on hold is normally distributed with a mean of 2.5 minutes and a standard deviation of half a minute. All right, if 2.5% of the callers are put on hold for longer than X minutes, what is the value of X? What is the value of X? So you see how they give us a percentage, an area. All right, so again, I'm going to draw this on a piece of paper, what's going on here, and then show you how we're going to use the calculator to help us figure this out. All right. So let's say, now again, this isn't the standard normal, right? The mean wasn't 0 and standard deviation wasn't 1. So this is just some other random variable, x, that's normally distributed. Oh yeah, I forgot to say what it is. X is on hold time. Time on hold. All right, how long are these people on hold for? And they said it is normally distributed with a mean of 2.5 minutes and a standard deviation of half a minute, 0.5 minutes. All right, so I'll draw a little picture. So here's possible different, a number line for representing possible on-hold times. Got this symmetrical bell-shaped curve. Mean value of 2.5 minutes. And then underneath these inflection points, again, sorry, this isn't perfect, but these are 1 standard deviation away. So that's 3.0, here's 2.0, and so on. All right. Now we are told, that the 2.5% of the callers are put on hold for longer than X minutes. So the probability that capital X is longer, the wait time is longer than little x minutes, we're told that this is 2.5%. Find little x. Right, find little x is what we're asked to do. So let me draw that. Right, so little x. The probability that big X is bigger than little x. They're on hold for longer than X minutes is 2.5%. So that'd be over here, because the 2.5. I can't put it over here because this is a greater than. So we're talking about area to the right. We're talking about so basically area to the right. Area to the right is 2.5%. So that'd be some value over here, some value x over here, where the area to the right is 2.5%. I want to know what is this value, right? What's that on hold time? How many minutes is that? All right. Okay. Now, if the area to the right is 2.5%, that means that the area to the left of this value is 97.5%, or 0.975. You're going to need that. All right, because here's how you're going to find it. You're going to use what's called, now if you're given an area and you're trying to find a value on the number line, you're going to use what's called the inverse normal on the calculator. INVNORM. Let me show you what that looks like. Right. Pull the calculator up. So I'll go back to that distributions area, second distributions, and then you see there's normal PDF, normal CDF, and you see the third thing down. Inverse normal. This is where I'm given an area and I want to find a value on the number line. So you see area. Now area, you enter area to the left, kind of like in the tables. You enter the area to the left. So I'm not going to enter 2.5%. I'm not going to enter 0.025. For this area part, I'm going to enter the area to the left of my x value is going to be 97.5%, 0.975. And don't enter a percent, enter it as a decimal. And then what's the mean? Now again, it's not the standard normal, so the mean is not 0, the standard deviation is not 1. The mean for this distribution was 2.5, and the standard deviation was 0.5. Right, so it's area to the left, comma, mean, comma, standard deviation. That's what you're going to enter on your calculator to find these values given areas. And here's what it looks like. And you got 3. So this value of x is approximately, and they say round 2 decimal places, 3.48. 3.48. So what we're being told here, what we're figuring out is that if I were to pick a customer at random, the probability that that customer would be waiting on hold for more than 3.48 minutes is 2.5%. But that's the inverse normal. Right? You're given an area, you're trying to find the value on the number line. So 3.48 minutes. See inverse norm down here. They explain it all down here again. All right, so this is very similar. Right, very similar. I'll just read this one aloud. You can draw a picture if you want. Never hurts to draw a picture of those bell curves when you're dealing with normal distributions. All right, so 2,000 students took an exam. The scores on the exam have a normal distribution or approximate close to normal distribution, so we can draw a bell curve with a mean of 81 points and a standard deviation of 5 points. The middle 50% of the exam scores are between what two values? I will draw this. I will draw this because it's a little different. It's not area to the right or to the left. It's area between the middle 50%. All right, so on a piece of paper again. I'm going to use some symmetry here. So x, again, it's not the standard normal, so I'm not calling it z, I call it x. X is normally distributed, right? Now x is these exam scores. And it's normally distributed with a mean of 81 points and a standard deviation of 5 points. I'll draw this, right? Possible exam scores. You got this it's normally distributed, so a symmetrical bell curve above it. The value below the peak is 81. And then beneath these inflection points, 1 standard deviation below, 1 standard deviation above, that's 86 and 76, right? Okay. Now, they're asking for, they're giving us, they're saying the middle 50%. Now, we know that this is 68. All right, between 76 and 86, remember that's 68% within 1 standard deviation. So we're going to be in between those. So we're even further in. So again, using symmetry here, this is the middle 50%. They're asking then, what are these values? What's this value here? What's this value here? And I can find both of these with that inverse normal. But we're going to have to do it one at a time though. We're going to have to use inverse normal. So again, using symmetry, if this is the middle 50%, that means these two outer areas, right to the left of this bar and to the right of this bar, are 25% each to make a total of 100, right? Again, using symmetry. All right. So that means for this value, right, this left value, I'm going to use inverse norm with 0.25 as my area to the left, right? The area to the left of this value is 25%. But for this value on the right, I'm going to use inverse norm. And then again, you enter the area to the left. Well, you got the middle 50%, right? The middle 50%, and then you got 25 after that. So 50 and 25, I'm going to put 75% there. All right. So let me go to the calculator, and then with this mean and this standard deviation, mean 81, standard deviation 5. So I'm going to the calculator. Again, second, distributions, inverse norm. And this is to find this left value. Has an area of 0.25 to the left of it, 25%. The mean for this distribution is 81. The standard deviation is 5. All right, now they want us to round these to the nearest integer, whole number. All right. So this rounds to 78. So this value is approximately 78 on the left there. And I do the same thing on the right. All right, so second, distributions, inverse norm. Now the area to the left of this upper value in this region, this green region here, the area to the left of that is again 75%. So I'm going to enter 0.75, and then the distribution is the same mean 81, same standard deviation 5. That value, and rounded to the nearest integer, is 84. So we're talking 78 to 84. Right. So back here, so in the range from 78 to 84, those exam scores make up the middle 50% of the data. And again, they go through same kind of picture I drew there and all that. Great. I guess you didn't need to do inverse norm twice. I mean, they did. But another thing you could have done too was, hey, use the symmetry. That was 78, which is 3 below 81. And then use the symmetry. This value on the right side should be 3 above 81. 81 plus 3 is 84. Right, so you could have done that as well. Right, just using the symmetry. All right, and so I think that's about it. All right, I'm just going to do the instructor cheat on the rest of these because, yeah, just got to read and understand what areas they're talking about. Now this one's just probability. This isn't the inverse norm. This will be that normal CDF. All right. So. Oops, I don't want to do more instruction, I want to do cheat. You can't do cheat. I can do cheat. But yeah, this will be that normal CDF. So draw a picture of a bell curve, shade some area, figure out what area you're finding, the probability corresponds to area, and use that normal CDF. And I think all the problems the rest of the way are like this. Yeah, this is another one where you're doing the same thing. Just good again, you gotta read, pay attention. What's the mean standard deviation of the normal distribution? Maybe draw a picture, shade some area, figure out the area. Right. So also pay attention to how many decimal places they want you to round to. Right. That'll be also key. And then this one. Yeah, this is that inverse norm. You're given a probability, you're given an area under the curve, and you're finding values on the number line. I did more instruction again. All right, so again, you do that inverse norm here, and I think one more. And let me see. It's no different. Yeah, these are all no different than the ones I've shown you using inverse norm. Find a value on the number line. Alright, so that's it for section 6.2. And no different. A lot of those objectives are pretty similar. Alright. So hopefully this video helps guide you through it. When you go through it on your own, you're not going to see exactly the same problems in exactly the same order that I did. But all the objectives are the same, and the way you would do them, the way I would approach them are the same. All right, so hopefully you have a good time with that, and thank you for watching. Let me know if you have any questions, of course, and thank you for watching.